get this down.
Bye.
Okay, and I'm going to mute everybody. Okay, so that we don't have any background noise. Okay, good. I think we're almost ready to go there. I think I got everybody muted now. And let's see, got one more thing I want to open up here. That is, I have an Excel file that I've saved here. Let's see, kind. What's that? Oh, it's not working. Okay, that's open on my computer. So if you want, you can kill the lights so that it's a little easier to see in here. Both of them have a due date of July 12th. The reason why I did that is the same evening as the test, and I wanted to make sure that you at least got started and took a look at them. So all you need to do is at least take a try them, do your best on them, submit it, and then you can always go back after July 12th. You can go back on any of these homeworks. You can always go back and redo them to raise your grade. The point of the homeworks and the assignments is that you understand how to do the problems, how to, you understand the work, and so on and so forth. The homeworks and the assignments are not a test. You can work with each other on them. You can collaborate on them. I encourage you to use the discussions boards to work on them together. That's why I've been making up little threads where you could make comments about them and you could exchange information on them. So that's the way that they're intended. The only thing is that I put a due date on them to encourage you to at least try them by that date, because you need to look at those, because that's the material we're going to cover on the test. So you need to at least go ahead and look at that stuff and kind of get your feel for it. But you can always go back later and you can redo the homework for a higher grade right up until the end of the semester. Okay, now that's a good thing because that's 30% of your grade. I don't recall, it's either 30 or 35% of your grade or something like that on the syllabus is the assignments. So that means you start out with the potential for, without having to be a genius, to have 35% of your grade, 30 or 35% of your grade be 100%. So that's going to help you out if you stumble on a test or something like that. That's going to make up for a stumble on a test. So it's really worth going back and like doing them, by the due date, giving them a try. And like I said, I love seeing people that try it 5 times before they get 100%, because that means you've gone back each time and learned a little bit more. So if it takes 3 times, 2 times, 1 time to get 100%, if it takes 6 times to be 100%, it's still the same grade as far as the homework is concerned. So I really encourage you to go with abandon at them. Just try them and see what you can get out of them, because that way it's kind of like riding a bicycle. It's nice for you to look at me doing these problems, but unless you try them yourself and get that kind of, I guess, I don't want, yeah, I know your brain's not a muscle, but that kind of muscle, the equivalent of neural muscle memory, whatever that might be, unless you actually give that a try and go through the process, you really don't learn it quite as well as like go ahead and doing it. So I encourage you to go ahead and do that. Like I said, no matter what grade you get on it up until July 12th, you can always go back and do it again. I'm going to post another homework which has 1 or 2 problems on analysis of variance. They're going to have a later due date, but there's going to be at least 1 problem on the exam on analysis of variance. We're going to go over a little bit of that tonight. So tonight is going to be mostly review. We did analysis of variance quite a bit last week, so I'm going to go over that a bit again today, and I'm going to review some of the stuff we went on before. In fact, I'm going to start with a problem that came up for those of you that were online last night during the review session. Problem came up at the very end of the review session that covers a lot of bases as far as t-test is concerned. I'm not going to start with that right now. I'm going to start with some other stuff. But yeah, on homework 5B, let's see, we need to choose between. If it's a very large sample, you can use the z-score. In other words, if the sample size is 100, perfectly okay with you using the z-score because it's so. I'm answering a question for those of you that may not have the chat window open. Question was choose between a t and a z-score. Sample size was 100. You want us to use the t-test in this case, or assume a large sample and use the z-score. The answer to that is with a large sample like that, you can go ahead and use it, but it's so close. The z is the critical value for z is always 1.96, for 95% confidence or an alpha of 5%. So 1.98 is so close that it's pretty much in the same ballpark. Now, when you use the t-test, you're never wrong, right? The t-test gets closer and closer and closer to the z-score based on the sample size, okay, and the degrees of freedom, of course. So anytime you use a t-test, whether you use it on a small sample or a large sample, you're always right. So when you're dealing with a sample, the t-score is always the way that SPSS or SAS or R or any of the other statistical programs are going to work. They're always going to use the t-test for when the standard deviation is based on a sample, no matter what the size is, just simply because for them it's no more effort to calculate it using the t-score than the z-score. Of course, for us, normal human beings, it's like the z-score is a little bit more convenient because we don't have to go to a table to look up a different number for every different sample size.
But you said that if we have the standard deviation of a population, then we use the z-score.
Yeah, if we have the standard deviation of the population, then you should use the z-score, right? Because that's correct, because you have a handle on the true variability of the entire population. So when you have the whole population, use the z-test. Okay, anytime you're using a sample, anytime you're working with a standard deviation that you've calculated from a sample, the t-test is the right way to go. As a matter of convenience, if the sample size is very large, like say 100, you can use the z-score just for convenience.
And in the formula, to the x bar plus or minus z, it's 1.96 that we use, depending on the confidence.
If you know the population standard deviation, it uses z-score in your confidence interval. So you use 1.96 for a 95% confidence interval. The t-score for a sample size of 100 would be 1.98, right? Which is really what you should use. But for our purposes, if you have a sample size that big, I have no objection to using 1.96 just because it's so close, right? Especially if it's a sample size of 100, say 200. If you go to your T table, you'll notice there isn't even an entry for 200 because it's such a large sample size and it's so close to Z. It goes from 80, 90, 100, and then infinity, right? Which is the same as the Z-score, which is basically means the whole population. Okay, so let's get started on some examples here. Some of this stuff that we're likely to see on the test. And one of the things that we're likely to see is confidence intervals. Okay, well, we'll certainly see them. Okay, and there's a number of different ways different forms that we might see a confidence interval. Okay, so let me make this thing's upside down. Okay, so let's take a look at a couple of ways we might see this. Okay, so one of the ways that we might see a confidence interval is when we're looking, when we calculate a point estimate or a point value. Okay, what's a point value? A point value is the quantity that we get from a sample that approximates the mean or the true proportion. Either one of those are point values, mean or proportion. That's we're getting a value that approximates them. Okay, in the case of a numerical variable, that's going to be x bar, the mean of the sample. In the case of a proportion, that's going to be p cap, the proportion that we get from a sample. Okay, so once we get that value, so if I take a sample of 36 people and I get a mean of 100, right? My x bar is equal to 100. I'm never, in normal everyday statistics, I'm never going to know what mu is. I'm never going to know what the true population mean is. All I'm going to know is what I got from my sample. Right. So if I take a large sample, 36 is not a very big sample, but it's a decent sized sample for a lot of studies. If I take a sample size of 36, right, I know that for those 36 people, the average was 100. And I know that if I was careful about making sure the sampling was independent and it was random, that's going to approximate the mean. That's going to approximate mu. Problem is that I really don't know how close to mu that it is. Okay, I really can't even begin to estimate how close to mu that it is. Okay, so I need another way to define how well I know how well this approximates the mean. I can't just go say, well, I took a sample of 36 people and the mean is 100, so that's what I'm going to call the population mean. Okay, without qualifying it in terms of the level of certainty that I have. Among other things, if you tell someone the mean for this population is 100 based on this, you may not be telling them what the sample size is. And the result of 100 for a sample size of 36, if you took a sample size of 1,000, you would certainly think that that would be a better approximation of the true population mean, taking an enormous sample size rather than a relatively small sample size. Okay, so that if this information gets lost in the process, you really lose the level of certainty that you have about this. So we need a way to define our level of certainty when we do these calculations. Okay, and the way we do that is we're going to say that we did this calculation, we took this sample, we found the mean, and x bar is equal to 100. But I'm gonna qualify that. I'm going to say x bar is equal to 100, but I'm going to say it's actually there's a range plus or minus some margin of error. Okay, and that's something that you do in real life all the time, right? If you say to yourself, somebody asks you how much money you have in your wallet right now, right? Say, well, gee, unless you count it every time you get up in the morning, right? Or you're married and you have to check it anyway to make sure none disappeared, right? And you might say to yourself, I haven't looked in there recently, but I think there's about $80 in there, right? So if there's, however, you don't know exactly what it is, so you may mentally make the calculation. I'm 95% sure it's between $60 and $100. So if I go park in this lot and it's $40, I have to pay it in cash or something like that, I know I'm getting my car back, right? So, however, if it's $80 and you haven't looked in there recently and say, boy, I'm really not sure. I'm 95% sure it's between $20 and $100. Well, now I better look at my wallet before I park, right? Because I may not be getting my car back today, right? So this idea of using a margin of error to give us a range of certainty for the true level, the true number, the true point value for this population is an idea that is really based on real life. Okay, so now how do we calculate this margin of error? Well, we take advantage of our understanding of the central limit theorem. Remember that was on the last test, the central limit theorem. And the central limit theorem taught us something about the variability of populations and the variability of samples from populations. So one of the things that it taught us is that we can estimate what the standard deviation for repeated samples, in this case of size 36, if I took samples of size 36 over and over again, I could estimate that the standard deviation of all those sample means, right, is equal to the standard deviation of the population over the square root of the sample size. In other words, the bigger the sample size is, the smaller the variability of the values I would get if I took that sample over and over again. So the variability of the X bar that I would get for a sample size of 1,000 is much smaller than the variability for a sample size of 36. Okay, we can actually quantify that this way. So now we say to ourselves, okay, I'm going to, for the moment, say, let's say I got that mean right. It's exactly right. The mean is really 100, right? So if I took samples from this population, let's say the standard deviation for that sample was 10. Okay, actually, let's make it 12. Okay, standard deviation of that sample that I took with the X bar was 100 and standard deviation was 12 from that sample. So let's say that I said to myself, gee, okay, so now I know if I take if I assume for a second mu is really correct and standard deviation is really sigma and I got it right on the nose, well, I know that if I take repeated samples of size 36 from this population, which has a mean of 100 and standard deviation at 12, assuming I got it right, right? If I take, it's going to have a certain behavior. And the variability of that sample is going to be the standard error, which we're going to call the standard deviation of repeated samples taken over and over again. The standard error is going to be equal to 12, the standard deviation of the population, over the square root of the sample size. Sample size is 36. So this is 6. It's going to be equal to 2. So instead of standard deviation of 12 for the population, I have a standard error for the repeated samples of 2. So now I say to myself, since whether I get a sample that's higher than 100 or lower than 100 is completely random, it's chance. If the mean is really 100, half the time I'll get a sample under that, half the time I'll get a sample, a average over that. So I can actually draw this normal distribution of all these samples. And the way it's going to look is the middle is going to be 100. And within 2 standard deviations below the mean, I'm going to call it 80 for, I'm going to call it 96 for our purposes and 112. How's that working behind me? Is that working okay? Okay, 112. 114 rather for 2 standard deviations above the mean. It's really 1.96. I'm just rounding it off, right? So I'm going to call that 2 standard deviation above. I know 95% of the time my samples from this population are going to be between 96 and 100 and 104. Okay, so 5% of the time it's going to be outside of this range. 2.5% of the time it's going to be above 104. 2.5% of the time it's going to be below 104. Well, taking a step back, that's really nice that I know that. However, the problem is that I don't really know mu. The X bar is not really truly what the mean is. I'm just using that to demonstrate what repeated samples, if the mean true population were mu, was 100, what that might look like. So I can use this a different way. I can take my X bar now, and I can take my standard deviation from my sample or my population, and I can say to myself that, well, instead of looking at this as repeated samples, I'm going to look at this as where the true mean might be. In other words, I'm confident that even though this may not be the exact true mean, based on the same logic, I'm 95% sure that the true mean is between these two numbers. So it might be 97. If we're 97, it would be close to 100, be a certain number of standard deviations to 100 or standard errors to 100. If we're 101, it would be close to 100. But every once in a while, 5 out of 100 times, I might get the true mean might be outside of this range. So that's why it's a 95% confidence interval, not 100%, because some of the time, 20% of the time, 20 times out of 100, 1 time out of 20, not I will miss the true mean when I'm looking at this range. Well, that's unfortunate, but that's part of life here when we're making accommodations for the fact that we don't know that we're never going to know the true mean. At least we can quantify our level of certainty. And really, in a sense, we can also quantify our level of uncertainty. There's a 5% chance we're going to be wrong, right? So, and you can also go, and that of course we can go to a 99% confidence interval just by spreading this out further, right? And instead of using, for a large sample size, instead of using 1.96, using 2.58 for a 99% confidence interval. So how's this going to work? Well, when we have a numerical sample, okay, when we have a numerical sample, it's going to be, if our point estimate is X bar, Our confidence interval is going to be X bar plus or minus. And now I have two choices here. I can put in the z-score or the t-score times my standard error. Okay, so my standard error is going to be equal to sigma over the square root of n, if I know the population standard deviation, very rare, and it's going to be equal to standard deviation of the sample over the square root of n. If I know the population standard deviation, I'm going to use the z-score. So for a 95% confidence interval, that's going to be 1.96. If I don't know the population z-score, if I don't know the population standard deviation sigma, I'm going to use the standard deviation of the sample, which means I have to use the t-score. Since this adds a level of uncertainty, I'm only guessing at the population standard deviation by using the sample standard deviation. Since I'm guessing at it, well, gee, I have to accommodate that for that. So my t-value is going to be bigger than z. And since I'm multiplying it by my standard error in both cases, that means I'm adding and subtracting a bigger number from x, so my confidence interval is going to be wider. And my t-value is going to be dependent on the sample size. A small sample, t is going to be even bigger. Big sample, t might be a little bit smaller, but always bigger than z. It's never going to be smaller than z, which is 1.96. Now, we just had the question, well, if you got a sample size of 100, if I go to that table that we have, right, when you get down to degrees of freedom 100, right, you go across, it says 1.98, and then it goes to infinity is 1.96, which in other words means if you know the whole population, it's it's a z-score. So there's nothing in between. So what is that telling you? That's telling you if you got a really big sample size, you're so close to the same value for t and z that in a lot of cases you might just use z. That's great if you're using the table and calculating manually, right? The trite answer, whenever you're using the standard deviation of the sample, the correct answer is always going to be use the t-score. Okay, if your sample size is 1,000, if z is 1.96, right? The t-score for a sample size of 1,000 might be 1.9601, just a tiny bit different, right? But it's always going to be different when you're doing this, working with a sample. When you're working with a calculator, or you're doing this by hand, well, it's perfect. It makes sense. Hey, so close, I'm not going to bother with this. I'll just call it 1.96 and use the z-score because it's a really big sample, say over 100, right? So, but SPSS, SAS, all these other statistical programs, these vertical programs they use for statistics, they will always use the true t-score when you're working with a sample. Why is that? Because it's just as easy for them to do. It doesn't introduce a lot more work for them like it does for you. But the right way is always to use the t-score. But like I said, samples over 100, I'm not going to say you're wrong if you just say, let's use 1.96. Okay, so this is the way we calculate our confidence interval for a numerical value. Okay, how about a proportion? Okay, so for instance, say sample size is equal to 200, and we're going to say, what can we have a poll on? How many people like chocolate ice cream versus vanilla ice cream, right? So for instance, if you had to choose between chocolate and vanilla, chocolate is out of 200 people, and this population, 110 of them chose chocolate, and 90 of them chose vanilla, right? So the proportion, P cap, we don't know what P is, right? We don't know the true proportion of people that prefer chocolate ice cream in this population because maybe there's 1 million people in this population. We'll never know that. But we can take a sample of 200, random sample of 200 people from this population and calculate that proportion for that sample. So P cap in this case is 110 over 200 or 55%, 0.55. Okay, in that case, we can also calculate now, since the true proportion, whatever it is, let's say we got it right, it's 0.55. Since we're taking independent random samples from this population, we're going to get the same What is 110? Oh, that's the number of people that preferred chocolate over vanilla out of a sample of 200. I'll try and write a little bit clearer. Okay. Do we have a resolution issue? Because like sometimes if is it my handwriting? Oh God, okay. I can't do too much of that. And my yeah, okay. Over here? Yeah. Oh, it's hard. It's clearer on my screen than it is up there.
So under SE,
Yeah.
SD?
No, SE. That's SE also. Okay. And that's standard deviation. I'm going to try and make this darker because I didn't realize that because now looking back, I can see it's. See here, look how much clearer it is on my screen than up there.
Oh.
So at any rate, I'll try and make this a little bit clearer. Okay, so P cap is equal to 0.5. Now we the same deal here. If we resample this population, we're not going to get 0.55 again. We're going to get a number higher or lower. But it's going to be, again, central limit theorem. It's going to be distributed the same way. The only thing is that in order to calculate our confidence interval, we're going to say P cap plus or minus the margin of error. And again, the margin of error is going to be equal to plus or minus. In this case, it's a large sample size. And you can pretty much depend on whenever we take a proportion, we're going to take a large sample, 100, 200, or something like that. And one rule that we have is that chocolate or vanilla is always going to have at least 15 people in it, right? Either group is going to have at least 15 people. So we don't want to be in a situation where you take a sample size, of 200, and there's only 3 people that chose vanilla, right? That breaks the rule. That breaks our sample size rule. So the sample size rule is got to have at least, say, 100 or so, and there's got to be at least 15 people in each half of the groups for our proportion. So our proportion, our P cap plus or minus a margin of error. So since it's a large sample, we're going to use 1.96 times our standard error. Now it's a little bit tricky because now we're going to calculate our standard error differently. Our standard error is going to be equal to the square root of P cap P, which in our case is going to be P cap because we really don't know P, 1 minus P over the sample size, right? We're going to take the square root of that whole thing. In this case, that's equal to the square root of 0.55 times 0.45 over 200. And you're going to calculate that, and that's going to get multiplied by 1.96 and so on and so forth. Then you go ahead and plug that in there and solve that margin of error and add and subtract it to get your range, your confidence interval, 95% confidence interval for what you think P is, right? So that's the difference. That's the way we would calculate these two situations. That's the way we would deal with two situations where we're looking at confidence intervals. Okay, just about chocolate. Okay, I didn't mean to take your mind off everything by mentioning chocolate ice cream. Because, yeah, there you go. So at any rate, yeah. See, now I'm starting to think about chocolate ice cream myself now too. So at any rate, so now let's extend this. Let's take this a little bit further. Since we understand this, how samples behave, right? We're going to say to ourselves, well, what about if I want to demonstrate a difference between two populations? Okay. Now, let's say I go and I want to demonstrate there's a difference between the what was one of the things I just talked about before? Did I mention what was X bar? Yeah, I don't want to go to proportion yet. I'm gonna stick with this. I'm not gonna. Okay, I got it. Just looking back to see what I had done there. Go back one page. Okay, so now let's extend this a little further. Okay, so now I'm going to take 2 samples, right? I'm going to take a sample. This is sample 1, right? And this could be soccer players. And I take sample 2. It's a different group. This could be chess club participants. Okay, and I'm gonna say I want to know if there's a difference in the number of hours that they spend on the internet. So I'm gonna randomly sample. I'm gonna randomly sample 100 soccer. Say I'm gonna 36 soccer players, and I'm gonna randomly sample. Well, maybe I couldn't find that many people in the chess club. 25 chess club players. Okay. So, and I'm going to ask them how many hours they spend on the internet per week. Okay, so turns out that when I take the average for the 36 soccer players, X bar for the soccer players is equal to a couple hours a night, a couple hours a day, and let's say it's 14 hours per week, right? And for the chess club players, maybe they don't quite watch as much. Who knows? Let's call it 10 hours per week. Okay, so I don't know what the mean for soccer club players are and what the mean for chess club players are, because there are nowadays. When I was a kid, there was like 4 people played soccer. Nowadays everybody plays soccer, right? It just was not an American game when I was growing up. Nowadays everybody plays soccer, right? So there could be 40 million soccer players in the United States. I'm not going to sample all of them. I'll never know what the true mean is. So I took a sample of size 36, kind of puny sample for considering how many there are. I don't know how you would work this exactly, but let's suspend reality for a second. So I'm going to take 36 soccer players randomly, and it turns out that the mean number of hours that they spend on the internet is 14. That's not mu. That's just the mean for this sample. If I did this again, different 36 soccer players randomly chosen, it wouldn't be 14 again. It might be 13, might be 15. Who knows? Maybe it could be 14 again, right? But if I took it over and over again, I'd get different numbers each time, almost every time. So as it happens, I'm going to say to myself, gee, what about the standard deviation here? What's the standard deviation? Well, standard deviation for soccer players, let's say for our purposes, it's 2 hours. Okay, and let's say the chess club players a little bit more variability. Let's say it's 3 hours. Okay, is the way that this sample is distributed. Okay, so now I have 2 samples. I have the sample size, the mean, and the standard deviation for each of these 2 samples. Well, now, if I were to calculate given this information, I could calculate a confidence interval here, couldn't I? Right? I could calculate a confidence interval. Let's say, for argument's sake, that we would calculate it as x bar s plus or minus, and the t-score is what we're going to use here for a sample size of 35. T-score might be, I don't know, 2.1 or something like that. X bar plus or minus 2.1 times the standard deviation divided by the square root of the sample size. That would be 2 over 6, or 0.33 times 0.33. We'd calculate our confidence interval for this group here. Okay, and maybe it'd be between, I'm going to just speculate, 13 to 15 hours. Okay, and then I could also calculate my confidence interval for the chess club as well. And let's say, for argument's sake, it's 8 to 12 hours. Okay, so now I'm saying to myself, gee, it looks like the true mean for this group is in this range. True mean for this group is in this range. I wrote it very lightly on purpose for you guys that are freaking out because you can't read it right now. The mean for this group and the mean for this group, they don't appear to overlap. It looks like that we're 95% sure that this means in this and this means in this. So maybe I can say to myself that they're different just because the confidence intervals are separate. They don't overlap. I'm 95% sure that this is this wide. I'm holding up one hand, and 95% sure that this is this wide in the other hand. And they don't overlap. Now, if they had overlapped, well, it could be that that chess club is really is really 13, and it could be that the soccer players could be really 13 also. So maybe if they overlap, I'm not so sure that they're really different, the true population means. Keep in mind, we're always interested in the mean, the population means, not the sample means. That's really what we're after here, what we're after quantifying here and comparing. Okay, so problem with that is that there's a lot of reasons why that's a sloppy way to do this. A better way to do this is to examine the difference between the two means. Okay, so for instance, examine x for soccer players minus x for chess players, right? X bar for chess players. See how far apart they are. Well, the mean is 14 here, mean is 10 here. They're 4 hours apart. And then say to ourselves, well, in hours, it's 4 hours, right? But hours is not really something that I can quantify in terms of probabilities. How many standard deviations apart are they? How many z-scores, if it's a really big sample? How many t-scores apart are they if uh, uh, given that they're 4 hours apart? Well, in order to be able to estimate how many t-scores apart, how many z-scores apart these are, I have to take that 4 hours and divide it by the standard error, right? Okay, so the top's easy enough, right? That's easy enough to see. But what about the standard error here? Well, if I calculate, I got 2 hours here and a sample size of 36, 3 hours here, sample size of 25 for standard deviation. The problem is that the standard error, right, is not the same for these two samples. It's close. This one's 2 hours, this one's 3 hours. It's close, but it's not the same. So what can I use here for the standard error? Well, okay, so now we're at a choice. Now we're at a juncture where we have to figure out how are we gonna. The top part's easy. This is gonna be the number of t values apart or z-scores apart for a super big sample. The t-score apart is the difference between the two means over the standard errors, and that's the way that's the way we did confidence interval also. The number of standard deviations apart. That's the way we looked at all our distributions and proportions and so on. So at any rate, so now, in order to calculate this, I have to set up some rules for myself that make some sense. Okay, so what are the situations that I could be in where I have to calculate this standard error? Well, one situation which would be really nice, and I'm going to open this up over here. I'm going to put this over here. One situation would be nice is if I only had one sample and I was comparing it to a known value. In other words, maybe the United Soccer Clubs of America decided to survey all their members and find out how many hours they spent on the internet, and they got a value for mu. The value for mu that they got is say 12 hours, right? So they know that value. Whoops. I don't have the right one there. They know that value is 12 hours. And I'm only going to take one. I don't have the same luck with soccer players. I'm dependent on the sample for soccer players. So what is that? That's a known mu for one group, but a sample for the other group. A single sample t-test, right? If I have a single sample t-test, well, standard error is easy. I'm just going to use the standard error for the sample that I have, right?
But you have a known.
If I have a known mu that I'm comparing it to. In other words, population A, you had a sample. Population B, somebody told you what mu was. It's known. So you're going to compare the two, right? So that's one possibility. That's a single sample t-test. And we're going to try a few of those. Single sample t-test, right? Okay, that's one possibility. What's the next possibility? You got two samples, right? So now you have to reconcile the fact that the standard deviation for this group is 3, but it's only a sample size of 25, and the standard deviation for this group is 2, but it's a bigger sample size. How do you reconcile that? Well, we're going to pool those two groups, and we're going to do a weighted average of the two groups so that we can see what would be the best estimate for overall for what we're going to call the standard error? We're going to do that. Okay, first we're going to have one sample t-test. Okay, one sample t-test. The next situation we have is when we have two samples, but the standard deviation, in other words, the variance of the two samples is relatively close. What are we going to define as relatively close? Well, for our purposes, as long as one is not twice the other, we're going to call that relatively close. So that's a two sample test, right? Two sample t-test.
Okay, but the first possibility is that you know the mu for one population.
Right, but not for the other. So you only have a single sample.
Okay.
Okay. It's going to be clearer when we actually put this to work. So now we have two samples that we're going to do our t-test on, and we're going to calculate our standard error based on the assumption that the variances, the standard deviations, are equal. Okay. Now, what about if the standard deviation for this group was 2 and the standard deviation for this group was 5? Well, 2, 5, that's a big difference. One's double, more than double what the other is. So we can have a two sample t-test, right? Where the standard error is going to be based on the assumption on standard deviations of the two groups are not equal, right? Okay, and we could have one more possible variation, and that is when we're comparing two proportions. Okay, but we're going to put that aside for now. Oh, I could, yes. Well, actually, tell you the truth, I'll tell you what. I wasn't going to mention pair, but now that you brought it up, I should bring it up. Okay, so the other numerical version of this is that you have paired samples. Okay, well, what does that mean, paired samples? That means that basically that both values that you have represent, usually in most cases, a before and an after. Okay, so if you have patients that you want to know if they go through a smoking cessation program, and you ask them how many cigarettes do you smoke a day before the program, and then how many do you smoke a day after the program. There's two ways that you might consider doing that. And one is to get one group of smokers that you don't give the training to, get another group of smokers that you do give the training to, and just ask them both afterwards how much they're smoking. The problem with that is that if you don't know how much they started with, right, there's so much more variability in how much they might be smoking afterwards. Might be a lot of the people that were in your non-intervention group didn't smoke that much anyway, right? And the other group smoked a lot, so even though they improved, you'd lose it very easily. Well, how about if you take all of these people, you ask them how much you're smoking per day before, send them through the intervention, and then see how much they're smoking afterwards, and try and determine whether there's a difference. Okay, so you got a before and after for each person. So let's say that person number one, subject number one, he was smoking 20 cigarettes the day before. Now he's smoking 9 cigarettes. So now the difference is minus 11. Next person was smoking 30 cigarettes a day. Now he's down to 22, minus 8. He's reduced his smoking minus 8 cigarettes a day. So now, instead of looking at the before numbers, the after numbers, just pay attention to the differences. Okay, so now you take all the differences, column of differences, you average them. And let's say the average comes out to minus 4, right? Well, if the intervention didn't help, what would you expect the difference in the smoking before and after to be? If you didn't intervene, probably be the same, right? No reason for it to change. So your difference, you would expect your difference to be equal to 0, right? But when you look at the actual differences, you find the average difference, it comes out to be minus 4. You say to yourself, well, minus 4, that's different than 0, right? So I want to demonstrate that that's that difference is significant, right? That's not due to chance. So that's how we use paired samples. Now, how many samples are we actually working with when we do our statistics for the paired samples?
How many people?
Well, not the number of people, how many samples, how many sample groups am I working with? You've got before and after, right? But you're ignoring the before and after. All you're looking at is the differences. So how many columns of numbers are you actually averaging? Only one. And what are you comparing it to? A known number, 0, right? So you're going to compare this list of numbers, -9, +3, -4, -11, this list of numbers, their average and their standard deviation, you're going to compare it to a set value. So paired samples is the same thing as a single sample t-test, except the mean that you're comparing it to is 0, is always 0. No difference. Okay. Again, this is something that when we actually give it a try, will make more sense to you. Okay. So now, and then the last issue is proportions. I'm going to show you proportions, how you work it out and stuff like that. It's on that sheet that I had handed out. I'll bring that up in a little bit also, but we're going to take a look at that as well. So now let's move on to some specifics. Now, analysis of variance gets a little bit hairier than this. Okay, so I'm gonna hold off on that till we get towards the very end. Okay, so let's take a look at this. Let's actually give this a try. Yeah, I meant to upload. Let me upload some of this data so that you guys can work with it. Okay, kind, SAV. Yeah. Let me open up Blackboard. I'm going to upload some data that you guys can work with. And let me take this, the most useful of this, and see if I can't put it into here. Oops, that's not what I need. I need to expand this. Okay, chicken feed. Some of this stuff is from the textbook, actually. That's not the way my name is spelled, by the way. It's not my fault. Okay, sessions. Okay, and oops, I got the wrong one. What happened to 10? I know I put a 10 in here somewhere. There it is. Move it up to the top. Let me move this up to the top so it's easier for me to work with. Okay, so let me, oops. Okay, let me put some files in here. Okay, and now I have to go through the torture of doing this one at a time because Blackboard is just not capable of doing these all at once. We're not going to use all of these, obviously, but some of these are going to come in handy, I think. I don't know if I got this one. I think I got that one already. Okay, that's enough for now, I think. I can't see what I need to do here. I guess I still have to pick something out. Okay, let me say submit. Okay, you guys should have access to these data files. These are all SAV files for now. Okay, let me go back to where I was. And I'm going to open SPSS up. Are you typing anything now? The screen is not moving. Uh-oh. You guys see the screen moving behind me? Oh, okay.
No, it's fine.
Okay, all right, good.
Are you gonna give us SPS files for the test?
I will give you them. They're going to be a little bit of both, like a little bit of problem work. I'll give you at least one SPSS file that you'll have to use to work out, and I'll also maybe give you some outputs and ask you to interpret it. Okay, so yeah, I know it's gonna, anybody here play bridge? Guys online, you play bridge? That's such an old thing, right? I mean, that's like something you see in the Lucy episodes. They're going to go out to play bridge or something like that from the 50s. Bridge is not on the test on Friday. No one say no. So, so is that nobody plays bridge? Nobody plays like there's something called contract bridge where like you go out and they set up these hands and these things that hold they deal the decks out and everybody plays as they play around robin. You play with a partner, two pair of people against two pair of people. It's kind of, I guess it's kind of gone out of vogue and stuff like that a bit. But bridge is kind of a complicated game. You bid the number of suits, the number of rounds you're going to win, and the number of hands you're going to win, and so on. And you have to work with a partner, and then the partner's out. You got to work with cards that are turned over on the table. But it's a complicated game. And the thing about bridge is that when you're playing with a beginner, there's certain situations in bridge where, and it's probably true of a lot of games, hearts or pinochle. I don't know if anybody ever heard of pinochle here, or that was a big game in the stoops on Brooklyn in the 50s and 60s. But what a lot of these kind of games, chess, for instance, okay, that when you're playing with a beginner, what's obvious to someone that's played the game a lot and can move very quickly is not obvious to a beginner. And a simple situation, they will ponder it. They'll know what to do, but they'll ponder it for a long time because they're not sure what they're doing. So the problem is that I have to structure these tests so that I know you can do them, because I know if you're insecure using doing the calculations or using SPSS, that's something that in another few weeks you're going to be able to do in 5 minutes. It might take you 30 minutes to do on the test this time around if you haven't had a lot of experience with it. So I'm going to try and structure it so some of this, so I get a chance for you to so you do some of the calculations, but on the other hand, also structured so that some of the work is prepared for you. Like if I give you outputs from SPSS and you just have to interpret it, so we can get a little bit more done. Okay, so I'm going to open up one of these files in SPSS. Let me go back here. Open data. And I'm going to go in here. Okay, so I'm going to start with this file called new drug. Okay, so here we have a pair of drugs that a new drug that we're testing, and we have a control group. We have let's see, the control group, people that took the drug before. We have males and females. We have the result of the drug of the exposure to the new drug, blood pressure before and after. I'm actually going to uh, I'm going to get rid of the control group. I'm going to delete them. I can just highlight them like that. Right? See how I held down the shift key? It's going to highlight them like that, and I'm going to clear. I'm going to get them out of there. So I'm only dealing with people that took the drug. Okay, some males, some females. So one of the things I might be interested in knowing is how does the uh, uh, mean uh, uh, how does the how is there a change in the average blood pressure for each of the people that took it before and after? Okay, so I have the average blood pressure before. I have the average blood pressure after. I have each individual. I have their blood pressure before they took the drug, blood pressure after they took the drug. Okay, so now what kind of sample is that? Is that a single sample? Is that a independent samples, two sample test? Is that a paired samples test? Yeah, it's paired. It's the same person, a value before and after. So I'm really interested in is the difference between these two values. And there's a way for me to calculate that difference. There's a couple of ways I can do that. One way is I can go into SPSS. I can transform. I can create a new variable. I'm not sure why that did that. I can create a new variable, okay, and I can say, okay, compute new variable or recode into a new variable. Compute a new variable. I can give that new variable a name. Maybe I'll call it the difference. I can say take the before value, subtract the after value, take the after value, subtract the before value, or vice versa, and put it into this new variable.
Where did you get the?
I went to transform, and I could compute variable. I can recode into the same variables, recode into different variables. I'm not going to ask you to do that for this test. After this exam, I will go over that in some more detail, how to create new variables and do calculation with them in SPSS, create new variables, transform them into other kinds of variables, and so on. I'm not going to go over that now because I just want to go ahead and show you how we would actually go ahead and do this test. But I could make another variable here that would just be the difference, like 93 minus 85.9. So that would be whatever, 8 point whatever. And I could create an actual new variable. As it happens, I don't need to do that to do this test. I can just go up here to analyze, compare means, and I'm going to go, if I had that list there, I could say one sample t-test, if I had a column like that. But in this case, I don't have that column, so I'm going to have SPSS calculate it for me. I'm going to go to paired samples t-test. Okay, and it's going to ask me for the variables I want to compare, and it's going to be variable one is before. I'm going to use after for one, and before for two. Not sure that I'm hoping for positive numbers.
Does it matter what
No, it doesn't.
party you use it in?
Nope, doesn't. I just give you positive or negative t-score, but it's still going to give you the same value for t. Okay, so I'm going to click OK. Okay, so it's going to go ahead and do these calculations. Let's see what it did. Well, first thing it did was calculate a mean blood pressure for after the exposure and a mean blood pressure for before the exposure. And it's 28 people. It's always going to be the same number sample size because it's a paired sample. You have to have values before and after. Now notice that the standard deviations are quite different, almost double, right? Almost enough to say that they're not the same, right? However, we're not interested in those standard deviations. We're only interested in the differences, right? So let's take a look at what happens now. So what happens now is SPSS calculates the mean difference, takes each one of those 28 differences, before minus after difference, and calculates the mean is 13. I got a negative number anyway. The mean is negative 13. The standard deviation of the differences, right? Only one column of numbers, so only one standard deviation. You don't have to worry about whether or not the standard deviations are the same or equal for the two groups. So this is a single sample t-test. And what does it compare it to? It compares it to the number 0. So it calculates a standard error, which is based on the standard deviation divided by the square root of the sample size, which is 28, right? And get that standard error, okay? And once you have that standard error, you take your mean, the difference, your mean, which is the difference between the two, subtract 0 from it, which is the other mean, and divide it by the standard error. So what's your t-score? Well, your t-score is really big. Your t-score is -12. Well, that's an enormous t-score, right? So the probability that you would be wrong if you reject the null hypothesis is very, very, very tiny, right? So let's take a look at the confidence interval for the for the for this test. Okay, the confidence interval is how big the differences are. So if there's no difference between before and after, you would expect 0 to be inside this confidence interval. Is there 0 in it? No, it's -15 to -11. So there's 0 is not between these two numbers. So when we did this,
so different, you would expect 0 to be in it?
you would expect 0 to be within the confidence interval. In other words, you would expect that you wouldn't be able to say with 95% confidence that the different mean of the differences is not 0. Okay, so that's our t-score, and that's our p-value, the probability we would be wrong if we reject the null hypothesis. You can also look at that as the probability that you would get this big a difference if there was no difference between the two means, between the mean of the differences and 0. So this is, yeah, yes,
Then you would not
Point-
see 0.
0.05, right?
0.05, yes, less than 0.05.
So what is it?
You would not see.
Then you would see 0 if the p-value were greater than 0.05, you would probably see 0 between these two. So maybe it'd be -11 to +2 or something like that.
It's less than 0.05.
You won't see 0 within that confidence interval.
So
But the
if
t part,
p-value is greater than 0.05, then you reject.
less than 0.05. That's the probability of being wrong if you reject your null hypothesis. Okay, let me go back to, I'll come back to this a little bit, okay? Okay, so that's a paired sample t-test. That's the same as a single sample t-test. Let me do a single sample t-test. Analyze.
This is a pair. That was a pair.
This is a paired sample, but a paired sample t-test is really the same as a single sample t-test because you calculate the differences and you only analyze the differences. It's only one set of numbers, right? It's only a single, and you compare that to a difference of 0. Let's take a look at another way to look at, okay, compare means, one sample t-test. So now I'm going to take my, before I do that, let me get a look at this. We see that the mean of the group after blood pressure is 85.7. So I'm going to say to myself, okay, analyze, compare means, one sample t-test. So I'm going to take a look at the average blood pressure before. I'm going to move it into my test variables. And I know that the average is 85.77. I'm sorry, 99.2, right? So I know that there's another population I'm comparing this to, another group, that their average blood pressure of their entire population was 94. And I want to know, can I say with 95% certainty that the average blood pressure for my 28 people before is different than this other group who I know that their true mean is 94. So that's a one sample t-test. Okay, and you can do this manually, or you could do this using SPSS. So I'm going to go ahead and click this and just go ahead and calculate, and let's see what happens. Well, the difference, my t-score, how do I get my t-score? My t-score is going to be the difference between 92.22 and 94, right? The two values that I compared, divided by my standard error, which is 1.14, calculating standard error from the standard deviation of the sample. Okay, so my t-score is 4.5, 27 degrees of freedom. Okay, and my probability of being wrong if I reject my null hypothesis is less than 1/10 of 1%, less than 0.001. Reject the null hypothesis, right? Okay, so now, so this is the way we would do this in SPSS. Let me give you another example in SPSS. Okay, this time I'm going to look at independent samples. Okay, analysis of variance. I'm trying to remember what these things have in them.
And the null hypothesis was that they were equal?
Null hypothesis is that they're equal. I'm going to write out the null hypothesis this time around. Okay. Yeah, I got to reformat this data to make this work well. Let me open up a different set. Data, open data, and let's say I'm going to work with. Let's look at the Oscars. This is Oscar awards for the last who knows how many years, maybe from the beginning, right? So what are our variables here? Gender, the number of the Oscar when it was given out, the year it was given out, the age of the person that got it, and their birthday, birth month, all sorts of other kind of weird data for this. Okay, so I have gender here, male and female. I'm wondering whether the average age for males who receive the Oscar is different than the average age for females who receive the Oscar. Okay, so what do you guess? What's your guess at that? Right, we'll have to take a look, right? So, in other words, I'm looking at a numerical variable, age. I'm going to find the average age for this sample. It's not all the Oscar winners. It's only 170 Oscar winners, right? So I'm going to look at the average age for females who won the Oscar and compare it to a sample, random sample of males who won the Oscar. Okay, so I'm going to compare one sample, males, to another sample, females. That's a two-sample t-test, right? It's not males. It's not before and after you won the Oscar. It's not individual. It's actually two samples. It's males and females, and what the average age is for each of those two groups. So I'm going to go up here, analyze descriptive statistics. Just for the hell of it, I'm going to go into descriptives, and I'm going to say, okay, let's see. Actually, I don't want to do it that way. I want to do it this way. Analyze descriptive statistics, explore. Come up. It'll be obvious why I'm doing this. I'm going to put age into the dependence list because that's going to be my numerical variable. That's what it's going to calculate the mean of, and I'm going to factor it by the gender, whether the person's male or female. Now I'm going to ask it to go ahead and calculate that. Okay, and let's take a look at our descriptive statistics. Well, the average age for the female Oscar winner is 36 years old, and for the male was 43.82 years old. Okay, well, what's the standard deviation for the age of female Oscar winners? Well, it's 11 years, very wide range. How about for males? Well, let's see. For males, the standard deviation is a bit narrower, 8. Now, 8 versus 11. Would I normally, if I'm going to do this manually, would I consider that equal variances or unequal variances? Equal, yeah, I do use the calculations for equal variances. I'm going to go through a problem of that before we finish up tonight. So let's take a look at this. We're defining for our purposes. They're never going to be perfectly equal. I'm just saying this for people online. We're going to define equal variances if the standard deviation of one group is not twice the other group. If it's less than twice the other group, then we're going to say that for our purposes, we're going to assume equal variances. We're going to pool the standard deviations in order to calculate the standard error. Okay, so an SPSS is going to do the same thing. In fact, SPSS is going to calculate it both ways every time so we can make our own judgment. Okay, so now the question now becomes, I got 44 years old for males and 36 years old for females, and it's not such a big sample size. Can I with with 95% certainty, with less than 5% chance of being wrong, can I say that the true mean for all males and the true mean for all females is different? Can I say that at the level of certainty that I would like? Okay, so let's do our hypothesis test. Let's set up our hypothesis test. Okay, so what kind of t-test is this? This is a one sample, two sample t-test, right? Two groups. Okay, and okay, let me write that down. So this is a two sample. I'm purposely pressing harder now. T-test. Okay, so are we going to assume equal variances or unequal variances? Equal variances, okay. Okay, so it's a two sample t-test. In SPSS, so our null hypothesis, right? What's our null hypothesis going to be?
They're the same.
That the two of them are the same, not the x bars, that the mu for males, mu h for males is equal to mu h for females, right? And what's our alternative hypothesis?
That they're not equal.
Right, mu for males does not equal mu for females. Okay, so now, just so you know, if we had reason to believe that the h for males could only be larger, not smaller, we could do we can do a directional version of this, in which we say to ourselves, well, it can only be male can only be smaller rather than larger. So our null hypothesis is that mu for males is equal to or greater than mu for females. And then our alternative hypothesis would be mu for males is less than mu for females. We could set this up differently. That's a single-sided test. Single-sided test is a less rigorous test than a two-sided test. Why is that? Because when you say that you're going to do a single-sided test with 95% certainty, that means that you're perfectly willing to have all the uncertainty on one side. So that's 5%, right? When you do a two-sided test, you have to split up. You don't know whether it's going to be which one is larger than the other. So you have to split up your uncertainty. So it's only 2.5% on this side and 2.5% on this side. So your t-score has to be further out before you can reject your null hypothesis. So a two-sided test is a more rigorous test. Okay, and most of the time it's hard to justify using a single-sided test. How do we know for sure? How do we know, with a drug, you might argue, well, this drug's a vasodilator, so it can't possibly increase blood pressure, but then maybe it has some other effect that could do that. Who knows? But so in other words, you have to make that's a lot of assumptions. So we're going to stick with two-sided t-test for most of what we're going to do. Okay, so now I have to just figure this out. Now the next thing I need to know is what level of certainty we want. So I'm going to say alpha is equal to 0.05. I'm willing to accept up to a 5% chance of being wrong if I reject the null hypothesis. Okay, let's go back to SPSS and actually do this test now. Analyze, compare means. Okay, it's not a one sample t-test. It's an independent sample t-test. Okay, and notice it hasn't asked me, do I want equal variances, unequal variances? So I'm going to move age into my test variable. That's the variable we're going to calculate the mean for. And into my grouping variable, I'm going to move gender. Now it asks me to define the groups. The reason why it does that is because in this case, in gender, you only use t-test for two groups, compare two groups, two means. In this case, gender, female and male, there's only two groups by nature of two groups. However, you could have another version of this where you want to compare the means based on hair color. And let's say there's 6 different kinds of hair color that might be represented. You might want to only compare brunettes to blondes, right? Or blondes to everybody else to see what age they got an Oscar at. So in that case, whoops, didn't mean to do that. In that case, you'd have to tell it what values you wanted to compare. 3 for blonde and 5 for brunettes or something like that. Now, I'm going to take a wild guess at this and call it 1 and 2. And if it doesn't work, I have to go back and actually look to see what the numbers are. I should have checked before. Well, could be either. Okay. So, but I'll give you what you need to know. I'll let you know. I'll give you like the coding, let you know that it's 1 and 2 or something like that. Let's see what we get. Did I get lucky? I think I got lucky. Okay. There we go. Okay. So it did the calculation again for mean and confidence interval and so on for each of the two groups separately for females and for males. Then it did a little stem and leaf plot. Then did box plots. Look at the males, right? It's a couple of outliers, right? For males and females, right? Okay, but let's take a look at what we wound up with our t-test. Why wasn't it produced? Let's see, mornings, and it's not produced because at least one of the groups is out. Oh, I guess I was wrong. Let me go back. Okay, we go back to the data view. Yeah, Oscars. And let me look at the variables and gender. Oh my goodness, look at that. It's a string variable. That's what it is. Oh, hang on a second. Okay, so I've never done this before this way. I've always used numbers. Let me give this a try. Analyze, compare means, independent samples t-test. And I'm going to define the groups. And the groups are female and male. See if this works. Okay. Oh, it worked. Okay. So normally we like to use numbers 1, 2 because you avoid typos and stuff like that. But in this case, yeah, M and F would have been in there too. But as it happens, it was literally males and females. Okay. So let's take a look at this. Here's our two means as they were calculated before, standard deviations. So let's look at our t-test. So if it's equal variance is assumed, the t-score is negative 4.9, almost a t-score of negative 5, right? There's our degrees of freedom and our significance, the p-value, the probability to be wrong if we reject our null hypothesis is 0.000. That really means less than 0.001. It's not really ever 0, right? So can I reject my null hypothesis? Yes, because this is less than my alpha is. And my t-value is less than my critical value of t. With a sample size this big, what do you think your critical value of t, if you looked it up on a chart, would be? Critical value of t would be like almost z, almost like z. It would almost be 1.96, right? The t. This is the value of t that you calculated. The critical value of t is the value of t that you have to exceed to have less than a 5% chance of being wrong if you reject the null hypothesis. And that critical value of t you get from your t-table. Based on the degrees of, sample size, degrees of freedom. Yeah, sample size 168. Now how did that get calculated? Remember that form we were looking at earlier?
N1 plus N2 minus 2, right?
Yeah, hang on a second. Let me see. Yes, exactly right.
Do we need to know that?
Yeah, well, you don't need to know it here because SPSS has calculated that for you.
It's just simplifying what you're saying.
Open. I think it was a PDF file. It wasn't a Word file. T variations. Okay. Come on, open up. Here we go. Okay, so if we look back at our variations here, the variations of this test, when we're working with equal variances, we're going to calculate our t-score, the difference in the two means. Oops. Here we go up here. The difference of the two means divided by the standard error. Standard error is based on a pooled standard deviation. We have to calculate that and then put that into this formula and calculate standard error, which is on the bottom here. But the degrees of freedom is simple. Okay. N1 plus N2 over 2. We're going to do this calculation in a little while. We're going to actually physically do it. Now, if we assume that the sample standard deviations are not equal, we would use this formula to calculate the t-score. T-score, the number of standard deviations apart that these two means are, going to be the difference in the means over, and again, now you're using the two standard deviations, your samples, but you're using them this way. Problem with this one is now, even though your standard error calculation is simpler, your degrees of freedom calculation is complicated. So a lot of people will say, I'm not going to bother with that. I'll just call the degrees of freedom the samples, smaller sample size, -1. Okay, so now what is that all about? Where do I find that critical value of T? From the T table, exactly. And I'm going to go to my desktop here and get my T table. And here's my T table. So for a sample size of 168, right, and a 95% confidence interval, 5% alpha, my T value is going to be damn close to the Z, which is 1.96, right? So this is the number I would have to exceed to reject my null hypothesis. And my T-score of -4 point whatever, it exceeds that easily, right? Sign doesn't, you don't have to worry about sign, just the magnitude of the number. Okay, so that's the number exactly right. That's the number we have to exceed in this case because it's such a large sample size. A smaller sample size would be a smaller number that we would have to exceed. Okay, so now I'm going to go back. I'm going to go back and take a look at my output from SPSS again.
So
Yes, I'm
the
listening.
T value, what number are we looking at in this independent sample?
I'm going to go back to it.
Oh, okay.
Go back to the output. There's the output again. Okay, so let's take a look at this a little bit closer. Okay, so there's two lines here. There's two lines here because SPSS always calculates both with equal variances assumed and equal variances unassumed, not assumed. Which one did we say we were going to use?
Equal.
Equal, because the two standard deviations are less than double. They're close enough that one is not more than twice the other, right? So that's the reason why we're going with that top line. SPSS gives you a better reason not to go with that top line. And it actually does. See these first four boxes here? See how it's separated from the rest? Okay, it says Levine's test for equality of variances. And it gives you an F score, which is a statistic, and it gives you a significance, which is like SPSS, it's a probability of being wrong if you reject the null hypothesis. When you test the equality of variances, your null hypothesis is that the variances are the same, that they're equal, right? So you would use the top line unless the significance value here, the p-value here is less than 0.05. So it's not less than 0.05. So SPS agrees with us. Stick with the top line. If this were less than 0.05, we would reject the idea that the variances are equal and go with the bottom line, which is equal variances not assumed. And we would go with this t-score, which is the same. But the degrees of freedom is different. Why are the degrees of freedom different? Why is that such a funny number? Remember, in unequal variances, we had to do that comp. Well, SPSS, instead of just saying, I'm going to take 85 minus 1, call it 84 for my sample size, like we would do, it actually calculates it out. And that's what that calculation comes out to. But again, the p-value is less than 0.05, so the result is the same. Right? In both cases, you would reject your null hypothesis. Okay. Now, we could calculate this using SPSS, or we could take the means and the standard deviations and use the formula here, right? Means and standard deviations and the sample sizes. That's all the formulas. That's all we need in these calculations to do this manually. Now, there was a problem that a lot of people had on the homework, number 11, 9 through 11 or something like that. Yeah, something like that in 5B. And I will go through that later on. Okay, so now proportions, I'm not going to play around with that in SPSS. We've gone through a few examples of using of calculating confidence intervals for proportions. You could also do a t-test for proportions. For instance, if you, let's say you wanted to compared the proportions of Democrats and Republicans who like chocolate ice cream, right? So you randomly selected 100 Democrats and randomly selected 100 Republicans, and you found that P cap for Democrats is 55%. P cap for Republicans is 65%. More, they seem to prefer chocolate ice cream more, right? Well, are you sure your null hypothesis in that case is P cap for Democrats is equal to P cap for Republicans? The proportion of Democrats that prefer chocolate ice cream is equal to the proportion of Republicans that prefer chocolate ice cream. I'll write that out. Okay. P cap for Democrats. Okay, so Democrats, 110 out of 200 prefer chocolate ice cream. That's equal to a proportion of 0.55. For Republicans, right, so that's 0.55. For Republicans, I'm going to call it, I'm going to change the number a little bit. I'm going to call it 120 out of 200. Okay, so for Republicans, the proportion that prefer chocolate ice cream is 0.60. Okay, so now do Democrats, all Republicans, if I were able to find out what the true p-values for these two populations were, would there be a difference between the two of them, right? Well, the problem here now is I have to compare these two, just like I did before. So I have to calculate a t-score. I have to compare these 2 point values and then see if they're far enough apart, enough standard errors apart for us to consider them different. Okay, so what is my null hypothesis here is going to be? My null hypothesis here is going to be P cap for Democrats is equal to P cap for Republicans. My alternative hypothesis is going to be P caps for Democrat does not equal P cap for Republicans. So now I have to find a t-score for this. The difference between P cap for Republicans and P cap for Democrats over some standard error that I have to calculate. Okay. Now again, now I have the issue here that I have two proportions, right? Not just one proportion. So calculating my standard error is going to be a little bit different than that P times 1 minus P over N now, right? Different sample sizes, could be different sample sizes, could be different proportions, and so on and so forth. So how do we figure that out? Well, the deal here is that we still calculate the t-score after we figure this out. And if the t-score is greater than our critical value, and what is the critical value of t for alpha is equal to 0.05 when we have a large sample size? The critical value is 1.96, right? Because whenever we're doing this, we're dealing with a larger sample size for proportions. How do I calculate what the t-score actually is? Yep. Okay. How do I calculate what the t-score actually is? Well, if you go over here to this last page, we actually have a formula for calculating what this t-score is. Actually, we call it z since we know we're dealing with large sample, right? So how do I calculate the difference between the two proportions divided by the square root of p cap, which is, well, what is p cap? P cap is a pooled proportion, which is P cap 1 times N1 plus P cap 2 times N2 over N1 plus N2. It's a weighted average, basically. Okay, so I'm going to take that P cap, which is going to be basically.
Are we doing this all by hand?
Yes, this one we would do by hand. There's a way to do it at SPSS. I'm not going to get into that for now, but chances are I'm not going to ask you to do. I might ask you to do a confidence interval for proportions, but I just want you to be aware that just like everything else, you can find a z-score, t-score, z-score, for the difference in these two proportions. And if your z-score comes out to be bigger than your critical value, 1.96, you can reject the null hypothesis. Exactly right. You can reject the null hypothesis and accept the alternative hypothesis. Okay. In the last example, we rejected the null hypothesis because the t-score was like 4.5 or 5 or something like that. It was way bigger than we needed, and the p-value, the significance, was 0.000, way less than 0.05. So we were able to reject the null hypothesis. Okay, so let me just play around a little bit with analysis of variance now. Okay, so I'm not going to go through. If you'll notice that in Blackboard. Tell you what, I'm just going to show you this quickly, and then we'll take a break. Okay. Okay, let's go back here to sessions, and I duplicated it for this session, but yeah, it's in last session also. Okay. You have demonstrations of using analysis of variance, doing it, first of all, kind of like the overall concept, then how to do it using Excel, then how to do it using SPSS, right? So you have a couple of examples of actually how to do this with small samples, right? And the idea with analysis of variance is just like the t-test, you're comparing the means of different groups, right? Different samples to see if you can say with 95% certainty that the means are different. You reject the null hypothesis, say that the means are different. The difference with analysis of variance is that with analysis of variance, you can compare more than two groups at the same time. T-test, you can only compare one group to a known value, single sample t-test, or two groups to each other, independent samples t-test, right? So analysis of variance allows you to compare several groups at the same time. You could conceivably use the t-test to compare several groups, like group A, group B, group C, group D. Let's say you want to know if the average age of these four groups are different. You could say, let's use a t-test to compare group A to group B, right? Well, there's 5% chance of getting that wrong. Now let's compare group A to group C and group A to group D, right? Well, now we got to compare group B to group C and group B to group D and then group C to group D. So we have to do many iterations, many times we have to compare in order to use a t-test. And each time you do that, number one is laborious, and number two introduces more chance of being wrong and rejecting the null hypothesis incorrectly, making a type 1 or alpha error. Okay, so which is bad. We don't like those kind of errors. So we need another tool. An analysis of variance gives us that other tool. Okay, and I'm just going to quickly show you here. I'm going to open a new database. Open data. See if I got something that would be suitable for this. Okay, so these rats have been fed different diets. Okay, so let me see. Tumor free. Did I get the right one here? I think I got two versions of this. Rat ID, fat level, tumor free. Oh no, I got the wrong one. Let me try this again. Open. Open. Data. Let's ask. How about chicken feed? Let's use that one. Okay. So these chickens were fed different diets. This is horse beans, linseed, soybean, sunflower, et cetera, et cetera. It's a number of different kinds of materials that they were fed. And at maturity, after 6 weeks, 8 weeks, I don't know how long it takes to grow hens for the market, but after a certain period of time, they were weighed. Maybe this is, I guess, ounces, I guess, right? That'd be 10 big bird, 10-pound bird. Yeah, 10-pound bird's a big bird, right? Maybe the turkeys, who knows? So at any rate, so I guess you could get a 10-pound chicken, right? Oh man, this one's 20 pounds. Let's say the turkeys, right? So they're given this feed for a certain period of time, and this is the amount of weight that they attained at the end of that period of time. So let's compare just by looking at the numbers, analyzing descriptive statistics. Okay, explore. Let's take a look at the relative weight given different kinds of feed. So I'm going to move the weight into here, and I'm going to move the variable feed into the factor list. Notice that that's a nominal variable. This is numerical. So we're going to find the average weight broken up into different categories of stuff they were fed.
So that was analyzed.
Yeah, analyze descriptive statistics. Explore. It has to be explore if you want to be able to break it up into different groups. And here we go. So we can see for each group that the average weight that hens that were fed this much was 323. Whatever horse beans are, 160. Linseed bean seeds, meat meal, soybean, sunflower, all the different different materials that they were fed. Now, we want to compare these means. Well, it looks pretty obvious to me that horse beans didn't do as well as, say, casein and some of these others. But do we have, can we say with some statistical confidence, with 95% confidence, that casein is different than horse beans? Looks like we got a shot there. Well, how about different than linseed? Looks like we got a shot there. Well, how about meat meal? Well, it's getting closer. How about soybean? That's so close too. How about sunflower? Well, maybe not, but they're awfully close together. How do I compare these means to each other without having to do the t-test like 12 times, right? Well, that's where analysis of variance comes in.
Sorry. So when you did explore, what went in the dependent list?
Analyze,
Uh-huh.
descriptive statistics, explore. Okay, into the dependence list is the number that you're going to find you're going to calculate the average, the numerical variable, which is weight. Into the factor list is the groups that you're going to break it up into. So that's a nominal variable, right? Like that could be male or female. That could be ethnicity. That could be, in this case, what type of food that they were fed. Okay, so I'm going to go ahead and take a look at how I might analyze this now. Well, if I go up here, analyze, again, I'm comparing means, even though it's called analysis of variance, right? I'm going to go over here and I'm going to use one-way analysis of variance because it's under that column, compare means. Okay, so I'm going to stop here. We're going to take a break and I'll leave you in suspense. And in fact, it might not be a bad idea. Let's say we're going to come back at 7:30, right? About 20 minutes from now, 7:30-ish. Okay, so you guys at home, give this a try and see if, yes, analysis of variance, at least one problem on analysis of variance will be on the test. Perhaps I might give you a output and ask you to interpret it, or I might not. We covered it last week too, and as well. And you have the videos and you have the stuff in the book on it as well. Okay, so let's take a break. Come back in 20 minutes, and we'll complete this problem. But you guys, if you have an inkling to do it, you might want to give it a try at home in preparation. Okay, so we'll be back. Bye.